Almost all familiar objects, including the sun, planets, rocks, and even you, emit what we call thermal radiation, meaning light that has a continuous spectrum that depends only on the object's temperature. This graph shows idealized thermal radiation spectra for a person and for stars of 3 different temperatures. In this video, we'll discuss the 2 laws of thermal radiation that explain the differences between the curves. Let's start with common examples. Volcanic rock is usually dark in color when cool, but as you see here, it glows red when it erupts as hot lava from a volcano. This tells you that the glow must have something to do with the rock's temperature, because its composition is obviously the same when it is cool as when it is hot. Here we see an incandescent light bulb, which has a coiled metal filament. When you turn it on, the filament glows with whitish light. The reason it glows is because the electricity running through it makes it very hot, as you can tell if you hold your hand near the bulb. In fact, the temperature of the filament is much hotter than the temperature of the red-hot lava erupting from a volcano. In other words, the white-hot filament is hotter than the red-hot lava. We can generalize these ideas by thinking about an iron fireplace poker. If you place the poker in the hottest part of the fire and let it heat up fully, it will become white-hot. Pull it back a little, and as it begins to cool, its glow will change from white to orange and then to red. As you pull it back further, it will cool until it stops glowing visibly. But it will still be much too hot to touch, and if you use an infrared camera, you'll see that it is strongly emitting infrared light. In other words, as the poker cools, its glow slowly shifts to longer wavelengths, from white to orange to red to infrared. You'll also notice that its total brightness decreases as it cools. These 2 ideas represent what we call the 2 laws of thermal radiation. The first law, also known as the Stefan-Boltzmann law, tells us that higher temperature objects emit more total light per unit area from their surfaces. That is why the fireplace poker is brighter when it is white-hot than when it cools to being red-hot. The second law, also known as Wien's law, tells us that higher temperature objects emit most of their light with higher average energy, which means shorter average wavelength. The fireplace poker is white when it is very hot because it is emitting a mix of colors that include short wavelength blue and yellow light. As it cools, it primarily emits longer wavelength red light, and when it cools enough, it emits only infrared light. We can be more quantitative by returning to the graph of idealized thermal radiation spectra. The horizontal axis plots the wavelength of light. Visible light is the narrow band marked by the rainbow of color. To the left are shorter wavelengths, which are ultraviolet, and to the right are longer wavelengths, which are infrared. The vertical axis shows the relative intensity, or brightness, of the light emitted at each wavelength per square meter of surface area. Note that both axes use powers of 10 scales, so that we can see all the curves, even though the differences between them are quite large. We see the first law of thermal radiation from the fact that the curves for higher temperature objects are everywhere above those for lower temperature ones. For example, the 15,000 Kelvin star emits more total light per unit area than our 5,800 Kelvin sun. Notice that not only does the hotter object emit more total light per square meter of surface, it emits more at every wavelength, which is why its curve is everywhere higher. We see the second law from the fact that the spectra of higher temperature objects peak at shorter wavelengths. For example, the 15,000 Kelvin star peaks in the ultraviolet, the sun peaks in visible light, and the 3,000 Kelvin star peaks in the near infrared. A person emits only infrared light, which is why we don't visibly glow in the dark, but can see ourselves in the dark with infrared cameras. We can use these curves to explain the colors we see for stars and other objects glowing with thermal radiation by looking at the visible light portions of their spectra. For example, the sun emits white light because it emits almost equally across all the colors of the rainbow, and white is a mix of all the colors. The cooler star appears red because it emits much more red light than yellow or blue light. Now consider this question. What color will the 15,000 Kelvin star appear to our eyes? Will it be ultraviolet, blue, bluish white, or bright red? The answer is C, bluish white. You can rule out choice A because even though the spectrum peaks in the ultraviolet, ultraviolet light is invisible to our eyes. We see only the visible portion of the star's spectrum, which is a mix of all the colors, making the star whitish, but with more blue light than red light, giving it a bluish tinge. Keep in mind that because these curves show the intensity of light per unit area, the total light outputs of stars and other objects also depend on their sizes. For example, consider the two shoulder stars of the constellation Orion. Bellatrix has a much higher surface temperature than Betelgeuse, which means it emits much more light per square meter of surface. However, Betelgeuse is a supergiant star with a radius about 150 times as large as that of Bellatrix, which makes Betelgeuse the more luminous of the two stars. In fact, the difference in luminosity is even greater than you can tell from this photo because Betelgeuse is also farther away than Bellatrix. To summarize, most familiar objects, including stars, planets, rocks, and people, emit thermal radiation characterized by a spectrum that depends only on the object's temperature. Hotter objects emit more light per unit area across all wavelengths, and their spectra peak at shorter wavelengths. These facts mean that we can learn about an object's temperature from its spectrum, and sometimes just from its color. That is why the laws of thermal radiation are so important, not only in astronomy, but in many other sciences.